Let's say that we've got a position vector p, and it is equal to, or represented as a column vector right over here, 2, 1. So if we wanted to plot this, and that's what I will do, let's plot it. So if we were to plot it, that's my y-axis. This right over here is my x-axis. So if we assume that the first entry here is the x-coordinate, 1, 2, comma 1. So our position vector is going to be right over here. We could represent it in this kind of vector symbol, right, like that, where the tail is at the origin and it's the tip, the head, is at that point. Or we could say it's really representing this position right over here on the coordinate plane. Now what I want to do in this video is apply a transformation to this position vector. And the way I'm going to do it is I'm going to multiply our vector p by a matrix, and then the resulting product is going to give me another position vector. So what do I mean by that? Well, I could have a transformation matrix, capital T, and let's just say it is equal to 2, let's say it's equal to 2, 1, negative 1, and 2. So what happens if I multiply t times p? And let's do that right over here. T times p. So first, let's just make sure that this is actually a valid operation, that matrix multiplication or matrix vector multiplication is defined here. So let's just look at what t and p look like. We already know what they look like, so I'm going to copy and paste. Copy and paste. That is t, and this is p right over here. So copy and paste. And let's see, can we multiply a 2 by 2 matrix times a column vector like this, which is essentially a 2 by 1 matrix? Well, sure. As we know, matrix multiplication is only defined, or at least the conventional matrix multiplication is only defined, if the first matrice's number of columns is equal to the number of rows in the second matrix right over here. And we see there both of those are 2. So this is going to result in a 2 by 1 matrix. So this is going to result in a 2 by 1 matrix. Now what's interesting about that is that this is another column vector. This is another position vector. So you took this vector p, multiplied it by this transformation vector, and we're going to get another 2 by 1, which we could think of as a position vector, which we could plot. So what's essentially happened is this transformation vector has essentially given this point, it has given us a new point. So let's think about what that is. So this first entry here, we're essentially thinking about, we're going to deal with the first row and the only column, really. So let me use a color that I haven't used yet. So we're going to think about this row and this column. So it's going to be 2 times 2, which is 4, plus 1 times 1, which is 1, or this is just going to be equal to 5. And then for the second entry right over here, it's going to, for the second row, first column, it's going to deal with the second row here and the one and only column right over here. So negative 1 times 2 is negative 2. Plus 2 times 1, which is 2. Negative 2 plus 2 is just equal to 0. So now we have the position 5, 0, which is right over here. So 1, 2, 3, 4, 5. So we started with this point, this position vector, I guess you could say p, and it's transformed it to this other position vector, and I guess we could call this, why don't we call this p prime? So that if you wanted to draw them as vectors, this right over, or kind of in traditional vector form, that right over there is p prime, and this right over here is p. This right over here is p. This is p. Actually, let me make sure there's a prime. And this is p prime. And the way we got from p to p prime is using this transformation matrix.